Hi everybody, we're going to look at the summary for Chapter 8, and Chapter 8 is our work, energy, and power chapter. So we just finished working with Fermat and forces, and so hopefully everybody's excellent at figuring out what forces are working on an object. And now we're going to talk about what happens when you sum up those forces and you move an object in a direction. So we know that work is actually moving an object, and the definition of work is going to be the cosine of the angle where work was done, and we'll talk about that more in a minute, times its force and times its displacement. And it has to do with the force that worked in the direction of the displacement. And so basically, we know that work can be computed in physics when an object is moved. We've talked a lot about if people go back to the same spot, how they're not doing any work. So it has to do with your displacement. When we have talked before in class, we talked about Zach taking a puppy on a walk, and I'm just going to do my square here as the puppy, so to make things easier. And we talk about Zach is taking this dog for a walk in that direction. So he could displace the dog a certain number of meters in this direction, and he would apply a force. But since he's much taller than the dog, he is applying a force at an angle. And the only force that we're interested in is the force that worked in the direction that the dog moved. So this would be the force in the x direction, the force that we're looking at, and there could also have been a force in the y direction, and that force doesn't have anything to do with our displacement, so we're not going to look at it. So when we look at a force, we're looking for the angle between the force that did the work and the force that was applied. And that'll make a little more sense in a minute. And so Zach did some work, and the dog moved in that direction. So if we look at that, his force is applied in this direction, and the displacement was in this direction. So we can see, if we were to add these two arrows together, we would just basically put them one on top of the other. We would see that the angle that the work was done in was 0 degrees of angle, and we know that if we put the cosine of 0 in there, the cosine of 0 will equal 1. Sorry, cosine of 0 degrees equals 1. So we can see that when the displacement and the force happen in the same direction, it's simply the force applied times the angle. So that's if he was pulling straight on the leash, the force applied was in the same direction as the force of the displacement, then that would work. In this situation, he's applying it at a little bit of an angle. We'll say it's 30 degrees, so we would put in the cosine of 30 degrees times whatever force he put in, which would be in newtons, and times a distance that he moved it in, which would be in meters. So we know that the units for work are Newton meters, and we'll remember that a Newton is a kilogram times a meter per second squared. It's a kilogram accelerating, and times another meter. So if we remember that that can also be known as kilograms meters squared per second squared. And all of that, we all know that scientists want to write things in one letter, so it's also known as a joule. So our work is done in joules. If we looked at a force being applied in this direction, and let's say that the dog was pulling really hard and managed to make the displacement actually happen in that direction, we would see that the angle, we'll move our force arrow down here, the angle at which this happened would be 180 degrees. If we put that in our formula, we find out that the cosine of 180 is going to equal -1. And so if we change again, so suppose Zach just pulls straight up on that leash, He decides he's finished trying to drag the dog, and he pulls up on the leash, but he still walks in that direction. So all the force on the dog is upwards while the displacement is in that direction. Our angle here would be 90 degrees. And when we plug that into our cosine, we see the cosine of 90 degrees equals 0. So Zach is not actually doing any work on the dog if he's pulling straight up, but then displacing to the side. And we'll do some more problems on that as we get to it. So that is work. Work is moving an object and figuring out how much force was required to do that. The second part of our thing is energy. And energy is the ability to do work. And so it's also going to be measured in joules because we're just measuring do we have enough energy to make that work happen. And so energy, when we're talking about energy, we look at a whole system that's involved, and we can say that the total energy involved in that system is going to stay the same from the time it starts till the time it finishes. And that's from the first law of thermodynamics says that the energy can neither be created nor destroyed, it only changes form. So the forms that we're going to look at in this chapter are potential energy, which is the stored energy of a system. So when an object is not moving, and kinetic energy. And kinetic energy, just like when we looked at kinetic friction, has to do with things in motion. So for any given system, we can say that the total energy of the system will always equal the potential energy plus the kinetic energy of the system. We also have formulas for each of these for potential and kinetic energy. Potential energy, we talked about it being the stored energy. And so when we think about an object, we know that it will have a mass and that it will be accelerating. And if we're on Earth, it's accelerating at the acceleration of gravity, which is 9.81. And if we think about mass times acceleration of gravity, we know that that's also the force of gravity on an object. And we also know that energy can be stored depending on how high it is. So if you think about something falling on your toe from a couple centimeters, it doesn't have as much energy as something that fell from a great height from several meters. It would have more energy depending on its height. So potential energy is mass times the acceleration of gravity times height. Don't get this confused with force of gravity. Force of gravity is mass times the acceleration of gravity. And when we talk about kinetic energy, we know that that is equal to 1/2 or 0.5, however you like to write that, times the object's mass, because if it's in motion, it still has a mass. And then if we think about something being in motion, we always want to know what its velocity is. And in this formula, it's the velocity squared. And so if you think about this in terms of units, we would again have the mass, which would be kilograms, times the acceleration of gravity, which is meters per second, times a height, which is meters. So we talked about that being kilogram meters squared per second squared, so that equals our joules. And down here we also have kilograms times the units. Velocity is meters per second, but since it's squared, so are its units. Okay, so we could also say that the total energy of a system is equal to 1/2 its mass times velocity squared plus its mass times the acceleration of gravity times height. And so we'll do some problems working through this, and hopefully that will make it much more clear.